Next, we shall consider one example. Suppose we have to find the Hamming coded word corresponding to the data 0110. We can see the number of data bits m equals 4. Then what is the number of redundant bits which should be added according to Hamming code? To find out that, consider the equation 2 power n should be greater than or equal to m plus n plus 1. If n equals 1, the condition is not satisfied. If n equals 2, the condition is not satisfied. And if n equals 3, 2 power 3 is 8 and m plus n plus 1 is 4 plus 3 plus 1, 8. Thus, the minimum value of n to satisfy the condition is n equals 3. Thus, the minimum number of redundant bits that can be added to form the Hamming coded word is 3. So the number of data bits is 4 and the number of parity bits is 3. Thus total there will be 7 bits in the valid code word. So we shall position the bits from right to left. Now where to place the parity bit? The parity bit should occupy the position powers of 2 and the remaining positions are reserved for the data bits. So we can keep the data bits in the data bit positions 0, 1, 1, 0. Now we should calculate the parities. For that, we have already seen that every parity bit will take care of a particular collection of data bits. To find out which all data bits are to be taken care of by a particular parity bit, consider this. Every number can be represented as the sum of powers of 2. Hence, every bit position can be represented as the sum of powers of 2. Thus, 1 can be represented as 2 power 0, 2 can be represented as 2 power 1, and 3 can be represented as 2 power 0 plus 2 power 1, and so on. And here we have 7 bit positions. Now a parity bit at the position 2 power 0, that is the parity bit at the position 1, will take care of the data bits at the positions 3, 5, 7, 9 and so on. Similarly, the parity bit at the position 2 power 1, that is the parity bit at the position 2, will take care of the bit positions 3, 6, 7, 10 and so on, and the parity bit at the position 2 power 2, that is the parity bit at the position 4, will take care of the data bits at the positions 5, 6, 7 and so on. So here we have only 7 bit position, so we can see the parity bit at the position 1 will take care of bit positions 3, 5 and 7. And the parity P2 at the position 2 power 1 will take care of the bit positions 3, 6 and 7. And the parity P3 at the position 2 power 2, which is 4, take care of the bits positions 5, 6 and 7. Now how each parity bit will take care of their corresponding collection of data bits by calculating the parity by using either odd parity method or even parity method. Suppose we use even parity method to make the number of ones even. So the bit position 3 is 0, the bit position 5 is 1 and bit 7 is 0. What should be the value of P1 to make the number of ones even? It should be 1. Similarly, bit 3 is 0, bit 6 is 1 and bit 7 is 0. What should be the value of P2 using even parity method? P2 should be 1. And bit 5 is 1, bit 6 is 1 and bit 7 is 0. What should be the value of P3? It should be 0. So we have calculated the parities. Now we can add these redundant bits to form our valid code word. Thus our Hamming coded word corresponding to the data 0110 is 0110011. Now the data is transmitted. Suppose a 1-bit error occurs. How at the receiving side we are able to correct the error? Suppose the bit position 6 got corrupted and it became 0. At receiving side, from the received code word, the parity bits are extracted. Here from the cardboard we can see the value P1 is 1, P2 is 1 and P3 is 0. Now the parities are recalculated at the receiving side. Bit 3 is 0, bit 5 is 1 and bit 7 is 0 and P1 is 1. So the number of ones is even, hence the parity P1 is correct. Now coming to P2, bit position 3 is 0, bit 6 is 0 and bit 7 is 0, but the parity P2 is found to be wrong. The number of ones is not even, hence P2 is wrong. Now coming to P3, bit position 5 is 1, bit 6 is 0, bit 7 is 0. P3 is also found to be wrong. P3 is wrong, thus set it to 1, P2 is wrong, set it to 1 and P1 is correct, set it to 0. Now 1, 1, 0, this combination corresponds to bit position 6. The bit position 6 is corrupted. How it works? We have found the parities P2 and P3 are wrong. The intersection of P2 and P3 is 6 and 7. That is, the data bits common to P2 and P3 are 6 and 7. So we can doubt 6 or 7. But we have also seen that the parity P1 is correct. This indicates bit position 7 is correct. So leave 7. It means bit 6 is corrupted. So we shall correct bit 6 back to 1. So the actual data should be 0, 1, 1, 0. Now suppose a parity bit is corrupted. Let the position 1 got corrupted. It became 0. Now at the receiving side, the parities are extracted. P1 is found to be 0, P2 is 1 and P3 is 0. Now the parities are recalculated at the receiving side. Bit position 3 is 0, 5 is 1 and 7 is 0. The parity P1 is found to be wrong. Coming to P2, bit position 3 is 0, bit 6 is 1 and bit 7 is 0. Parity P2 is found to be correct. And bit position 5 is 1, 6 is 1, 7 is 0. Bit P3, parity P3 is also found to be correct. Since P3 is correct, set it to 0. P2 is correct, set it to 0. And P1 is wrong, so set it to 1. The combination is 0, 0, 1. This combination of parity bit corresponds to the bit position 1. It means bit position 1 is corrupted. The value should be 1. So we can see if a parity bit itself is corrupted, it affects that value because it is not taking care of any other parity bit. It just takes care of the data bit. So whenever a parity bit is corrupted, then that corresponding value of parity bit will go wrong. Now see what happens if bit 7, which is common to all collections, is corrupted. Suppose bit 7 is corrupted. At the receiving side, parities are extracted. P1 is 1, P2 is 1, P3 is 0. The parities are recalculated. Bit 3 is 0, bit 5 is 1, bit 7 is 1. We can see parity P1 is wrong. Then bit 3 is 0. Bit 6 is 1, bit 7 is 1. Parity P2 is also wrong. Bit 5 is 1, bit 6 is 1, bit 7 is 1. P3 is also wrong. P3 is wrong, set it to 1. P2 is wrong, set it to 1. And P1 is wrong, set it to 1. Thus it corresponds to the combination 1, 1, 1, bit 7. It means bit 7 is corrupted. So we can see if bit 7 is corrupted, all the parities goes wrong because bit 7 is the one which is common to all the collections. So to find out the actual data, bit 7 should be corrected back to 0 and the remaining data bits can be extracted 1, 1, 0. Now this is our actual data 0, 1, 1, 0.